Okay, let's start the class. Good morning. Good morning, everyone. So last time we have discussed two examples, two case studies to show the impact of software architecture and the importance of architecture in the software engineering software system development. So basically, we showed one case study in the most successful program in the world, the World Wide Web system, and it has been evolved since it was created into Web 2.0, and currently it has been continuing evolving into the cyber physics networking system, right? So basically, in the future, with the evolution of the web-based system, everybody may have an IP. So everybody in the world may be an IP. So that's the trend, the trend of evolution of web-based system. So basically, we cannot describe the evolution, the architecture, and the design, and the entire styles or features through any piece of program that you can observe from the web-based system, right? So the only way we can describe and visualize its improvements and the evolution is through its architecture, right? So basically, we showed three examples of graphical architecture representations for different stakeholders who have different background in technology of computer science as well as the domain background. So basically, each of the visualization, the graphical notation, is tailored for a different perspective of concerns in the world. And on the other hand, we also found that only the graphical representations are not sufficient in describing the architecture of web-based system, right? So we have a lot of No. So I'm just doing a quick review of what we have captured last time. And basically, we have learned we need to add a lot of constraints, rules in the description of an architecture on top of the graphical notations in order to gain a comprehensive view, comprehensive understanding of how the architecture defines and what kind of quality features that are supported by this architecture, so that the future developer, the future maintainer of the system can continue evolve the system and maintain the system in its intended way, its expected way. And last time, let me go back to the computer, since students maybe more used to look at the slides when I'm describing things. So basically, last time, I also showed a small example on the desktop. So basically, it's a daily Unix command line system or command line instruction. So basically, we use everyday, which is the easiest command line instruction in Unix. But we can still describe its architecture. So people can understand its underlying concerns, underlying constraints, underlying rules. And on the other hand, it facilitates the reuse of each of the components, connectors in this architecture. So basically, that introduces the pipe and filter architecture style, which we are going to cover in the next few slides, in the next few lectures. So the final example I would like to go over is related to how we can effectively and efficiently develop our software system based on the architecture. So basically, this is called the product line. So a very good motivating example is from the small electronics domain by the small electronics company. I don't remember which company was that. The Philips, right? So basically, this company was originated by producing the television for different kind of customers all over the world. You know that the television have some common functionality. Basically, we can show the TV shows through the television. But the television system needs to evolve to accommodate different format, signal transmission format, the signal displaying format, from different regions of the world, right? For example, U.S. format is totally different. The signal representation format is totally different than those that are in China, in Europe, right? So on the other hand, we are going to evolve the system to make the TV set to be connected with all kinds of external devices. For example, we're going to connect it to the high definition DVD player, the Blu-ray system, right? And the audio systems, the computers. So all different kind of systems. You may or you may not expect that will be occur or will be emerge in our market. So how the Philips is the first one who has initiated the idea to architect their electronics products based on the product line architecture. So they try to maintain the commonality among all those TV sets, TV systems they are going to produce. So they found there must be some common functionalities which are very similar to each other, which forms their core features that most likely they're not going to be changing no matter how environments changes or how the stakeholders' requirements changes. So basically, that helps the Philips Electronics to quickly capture the market share by effectively and efficiently produce different kind of variations during the product evolution. So basically, they project the future evolution of the system into 3 dimensions to capture the potential variations of the systems. For example, different customers may have different price range requirements, right? So we have high-end customers, but we have regular and low-end customers, right? Which requires different complexities of the feature, different features. Well, some customers may want more fancier, advanced features, but some are just regular customers, which just wants regular TV sets. And also, the variation comes from the output devices that can be connected with the TV set, right? And the regions of the world which accommodate, which may have different signal processing format, signal displaying format. So basically, those 3 dimensions captures the diversities in terms of the image formats, image processing format, the sound format, the data processing format, the different kinds of user interfaces that are required by the users, the connectivities. So basically the connectivities with external devices. So by observing those 3 dimensions of potential changes, then we can design and devise our product family, product line architectures. So we are trying to build each of the TVs from that product line family instead of from scratch. Because if you try to build everything from scratch, you can never have any advantage in early capturing the market share. And the Philips is going to be out of business, right? It's not an efficient way of building software system. So our intention is to whether we can devise an architecture to help us reuse the existing structures as much as possible, even though the existing behaviors of the television system and reuse existing components of the system. So it's very important for us to simplify the development task first, right? And it also simplifies the testing work. So because we assume those parts, those common parts, reused parts, has been tested over and over again underneath different scenarios with different external devices. And also it significantly reduces the development time and the cost. And by reusing the existing architecture, it can also help us to estimate the development effort based on historical development experience, right? And we can recognize and exploit the commonalities and capture, also retain those variabilities in the architecture. So not only capturing the commonalities, but we need to expect some future variations in our architecture. So basically, this chart summarizes the ideas of using product line architecture as the big win in the software development. Because by proposing a specific architecture that are accumulated from the past development experience, it basically supported reuse, not only supported the reuse of structure, test cases, the patterns, but also it inherits the development knowledge, experiences, the ideas. So basically, even though when you try to evaluate, assess the feasibility of a project, if you start with the prior product line architecture, it helps you to provide the early prototype, early assessment of why you think this kind of development, this kind of architecture can support the success of the system, can make sure your system can be delivered within the time and the budget, right? So it provides not only the structural guidance, testing guidance, but also the engineering guidance to guide the project, the development effort allocation, the skill allocation of the system development. So basically, it provides the reuse of all kinds of well-practiced, well-worn experience from past. So the product family is kind of the reuse of the prior structure, behaviors, implementations, test cases, test suites, test harness, all those kind of things. And it also helps us identify which part of the system would be most important for your future development, right? So by recognizing all the common features versus all the potential varieties of the system, then we can compose different kind of variations of the system in an easy way, just like building a Lego. So it provides a quick divergence as well as the convergence at the end of the system development. So it immediately brought a quick win to Philips Electronics. So how can we visualize the product line architecture? This chart shows a very tiny example that are captured from a corner of the Philips Electronics system. So you could tell that the light blue rectangle represents the components in the product line architecture. Actually, the Philips Electronics system named their product line architecture. They brought up a very cute name for their product line architecture, which is called Koala. So, so this is a small piece of the Koala architecture that captures some common parts of the system. So you can tell we have several components in the system. We have 5 components in the system, right? And the connectors are between the components to enable, to show the communications between those components. And the direction, so you may notice that the triangles may be towards into the components or towards facing outside of the components. So basically, if the triangle is facing outside of the components, it shows something exported from that components. And if the triangle is facing into that components, it indicates a parameter or a data that are taken by these components. So basically, we showed something exported and something imported to that components. So each components may be attached into at least one inwards or at least one inwards or outwards interface that are connected connected with the connectors between the components. So on the other hand, the other beauty of using the product line using the architecture to describe the system design is that not only you could show the internal structure by showing the internal components, connectors, interfaces, but also you could consider the aggregation of all these pieces as one components that are interacting with the external worlds. So basically, it brings us hierarchical integrations of different parts of the system. So when you're trying to understand the system's interaction, communication with other components, with other subsystems in your entire software system. So in this case, if you consider all those 5 components and connectors as one big piece, for example, we can call it as a TV platform, right? So basically, if this is the core part, the core components, which captures all the commonality of the koala architecture, then can you tell me how many interfaces, how many pieces, what kind of information, how many pieces of data are required by these components, and how many pieces of data are exported by this component? Right. There are 3 data. There are 3 kinds of interfaces that are pointing towards these yellow components. So indicating that there could be 3 kinds of input that are required by these components. But usually, because we consider this part as an initiation of these components. So by excluding this initiation interface, we would have 2 interfaces that are facing inwards, the components, and the other 2 are facing outwards. So basically, those are considered the service that are exported by these components, but must be required by other components in the system, right? So from this chart, we could show how the product line architecture can be hierarchically represented, visualized, to show the aggregation of components and connectors. So on the other hand, we haven't shown, the only thing we haven't shown, but we're going to discuss in detail in the future, is the variabilities. How do we represent the variabilities of the architecture, right? So basically, the koala architecture supported the diversified interface. So basically, you can dynamically plug and play the system into other systems. Basically, we can dynamically determine what kind of interface, basically the input and the output and the inwards and outwards interfaces are going to be compatible with. So what format of data we're going to we need to take, and what format of data we're going to export to other systems. So those kind of determination can be done in the runtime of the system. So we could also provide some static switching type of interface. So basically, you could determine a specific type of data that can be compatible with our core components or with our external components based on static switches, right? So we will discuss those variability, those interfaces that can produce variability to accommodate defined variabilities when we define the architecture styles of the koala. So as a summary of the big idea of software architecture, the software system is complex inherently. So complexity is one of the essential difficulties that currently, even though with the emergence of the advanced software engineering and computer science techniques, we still cannot handle this. We cannot resolve this problem completely and even sufficiently. So the software architecture can have a good analogy with the building architecture. However, we also identified some difficulties, some differences between those two disciplines. But it's also a good practice when we talk about software architecture, we tend to borrow ideas from other disciplines, from civil engineering, from biology, from other kind of domains. So software engineers can learn from a lot of other disciplines, and they also need to develop and have developed a rich body of their own architecture knowledge that needs to be inherited and learned by the future architects and developers. So we do not want to lose those experiences. So basically, this is a discussion of big ideas. Is there any other questions before I proceed to the next topic? So next, we would like to put software architecture in the context of the entire life cycle of the software engineering development processes. As we have mentioned in the previous lecture, that in this class, we're going to take an architecture-centric approach. Basically, we're not going to use the software, we're not going to consider the software process as the end product of the software engineering, or we do not consider software process as the only principles that can guide us to build the correct high-quality software system. But we're going to show how software architecture as the essential role or essential deliverable artifacts in the software engineering development practice to show the success, progressive success of the products. So why architecture is important? Basically, architecture provides us a foundation, a fundamental basic understanding of what the software system is. So we consider software architecture is a set of principal design decisions about a software system. And there are three fundamental understandings of software architecture. First, we know that every application must have an architecture, no matter whether it's explicit or implicit. So most likely, especially in agile system development, architecture can be very implicit in developers' mind without being specifically documented, right? And every application has at least one architect who is leading the system development. But architecture is by no means just only a phase of the development. So this is an easy misconception that easily taken by most of our developers. So if we view architecture as a phase, so if we only think architecture starts from the design phase, then it denies its fundamental role in software development from the beginning of the system development, in understanding what the software system is and what are the specific requirements that should be proposed by the stakeholders. So architecture, although it is a high-level design, right, compared with object-oriented design techniques that we're going to go through in another class. So it's more than a high-level design, especially by putting it into other phases of development. So architecture is also represented by different kinds of things. Architecture can be represented by starting from the use case descriptions, right, to understand how the software system is interacting with the external world. And what are the major functionality, what are the expected behaviors from the systems. The architecture can definitely be represented by the structure models, right, by the class diagrams. the architecture can be also represented by the objects, even by the source codes. So most likely, developers are concerned the architecture in terms of their understanding, comprehension of the code, right? And even the architecture exists in the executables that are compiled from our source code. So we will going to put architecture in the context of different development activities, such as requirements acquisitions, the design, implementation, analysis, testing, evolution after the system is delivered, and we're going to summarize it as an entire picture of the development process. So why architecture? What kind of role that software architecture plays in the requirements phase, right? Traditionally, we consider the software requirements acquisition as a very independent forefront activities in the waterfall process models, right? So until we collect a complete set of requirements, we cannot start the design in the waterfall model. But this is not the case in the spiral model, in the iterative experiment, in iterative system development, right? Because it will impose a lot of risks if you do not, if you cannot completely understand the requirements, even though you consider you have complete the collection of all the requirements and specify them in a sufficiently rigorous way. But you could always encounter a lot of risks by not communicating sufficiently with your stakeholders. So some inconformance or some mismatches often emergent during the system development. You will find a lot of mismatches between your understanding of software system, software requirements should be, and what the client or the customers or end users understand. Or even though you think that they already clearly communicate their requirements, the customer themselves may not be able to clearly understand, clearly communicate what they actually want. So this is the challenge for software engineers. So basically, in the software system development, there is an implicit rule that everybody understands in the software engineering domain. It's called Ikiwisi rule. So I know it when I see it. It's very typical in the system development. The customer will not know what they exactly want until they see something. They see some prototypes. They see some of your design intentions. So this is one role that we could leverage from that software architecture can play, facilitate the communication and mutual understanding of the requirements. However, first, we know that without reference to the existing architecture, it would be very difficult for the customer to communicate their actual requirements. For example, it would be very difficult for them to give you specific features they require, specific user interfaces. And then the most challenging thing is that they don't know where they would like the system to perform. For example, how quickly they would like the system to respond to their request, right? So those kind of things, it's very difficult for them to specify before they see something or see some preliminary proofs. Question?
From where the proof, from portfolio, or you need to do some prototyping based on the requirement?
I think they can, from our prior experience, they can be done in both ways. So you can do early prototype, to simulate, to do some alternative simulations of preliminary features of the product. If you try to convince your stakeholder whether the adoption, for example, if you try to convince your customer, some components can be directly implemented using the commercial off-the-shelf components. Or I would like to reuse my prior developed components to fit into your system. But you would like to show the customer whether this design decision can meet their requirements, can meet their performance requirements, for example, right? Then you would like to demonstrate through a small simulation based on your prior components, right?
Isn't it like time-consuming rather digging into more requirement and getting into conclusion, getting a prototyping, and then digging into requirement?
I think those are, you consider it's really time-consuming, right? So iterative process is always time-consuming. So it's always a trade-off. How much is enough, right? So it's also a research problem. How much architecting is enough? And how much prototyping is enough things? So we are not going to do those prototyping and preliminary architecture for every components, for every parts of the system in terms of by considering the cost, the schedule of the prototype of the system development. But we would like to prototype those very critical, the key components that determines the success of the system, right?
So you mean like the prototyping the non-requirement rather than the complex requirements?
So we could show them the complex requirements, but if only the complex requirements, if it's the most prioritized, the highest prioritized requirements for the stakeholder. Yes, so those requirements and components should be prioritized by delivering the system. So this is related to how the project manager determine their architecture requirements acquisition activities. How do they allocate resources in different process activities, including prototype and early architecture. So so with the reference of existing architecture, it will help us to assess the practicality, the feasibility of the projects, to estimate the schedule and the budget of the projects, right? By showing and by proving from the prior system development experience. And it would be easier, for example, if you are trying to convey your requirements to your house builder. It would be easier for you to describe your requirements for the house in terms of how many storage I want, right? What kind of roof I want, whether I want a flat roof or the roof with slopes. And how many rooms, what kind of rooms do you want? For example, how many bedrooms I want, how many study rooms, how many recreation rooms, how many living rooms do I want? So instead of describing it, I want a shelter which can prevent us from the rains, snows, or what kind of temperature I would like the room will have. So it would be very awkward for you to describe your requirement without referring to those architectures, right? So, but in engineering, there is a dilemma in promoting the creativity and innovations in engineering assistant, in building a product. Some people may ask, if you refer too much to the prior development, too much to the prior architecture, can that restrain your future creativity, your future innovation of the software system, right? If you constrain yourself too much, or if you confine yourself too much to the prior system development practices, right? So this is a kind of a dilemma that a limitation of referring too much to architecture in the requirements phase. So in the origin of requirements acquisition, we try not to constrain our requirement specification with the existing design and existing architecture, because we also think it will confine our future innovation of the software systems, right? For example, the washing machine could be a very good example to show this. If you describe the washing machine in the way that people used to wash the clothes, in the very ancient time, people used a stick to hand over the clothes along the river. If you describe your requirements in this way, it confines yourself to the traditional way in washing a clothes. So the washing machines no longer be like what we are seeing here in nowadays, right? And but on the other hand, we do not want to describe the washing machine in the way that without referring anything, referring to the mechanics, how we wash the clothes. For example, do we want to describe the requirements as we would like to build a machine to ensure that the machine can clean some cotton materials or some kind of silk materials, and we would like the machine to achieve the goal of removing how many particles that are larger than basically the particles on the material in the cotton materials in a specific amount of seconds. So it would be very difficult or awkward if you try to describe the requirements without referring anything mechanics or referring the structure you expect from the washing machine. So existing design and architecture always provides us a very convenient vocabulary sets to describe what the product should look like based on existing solutions. And our understanding of what works now will help us to project what can be work in the future scenarios. So if there is any emergent needs in your organization to build a new software system, there must be some problem that haven't been resolved by the existing systems, right? So by showing how existing system works or not, we'll be able to better communicate with your stakeholders what their real needs are, right? So by showing them how it works now in the current business process, it will affect or it will even stimulate what your stakeholder understand what they really want in the future. So basically, what they really want is missing from what currently works. So those insights, not from nowhere. Those insights has evidence. Evidence are collected from our prior development experiences. So we show them the architecture and the design and show them the prototype. It's like it's the way we're showing them the evidence why we consider 5 milliseconds response time is infeasible. If we can show them by prototyping, by showing them our design option, if you select this is all available product, then can be used in these components, right? If we could show them nothing can achieve 5 millisecond response time, and whether do you need such a quick response time? Is it feasible or meaningful for you to achieve such response time? So by providing them evidence, it helps them to imagine what might work, what really needs, and enable you to convince your customer your design. So requirements analysis and consideration of design must be pursued in parallel at the same time, so they cannot be separated. So another challenge in requirements acquisition is the non-functional properties. So previously, by showing them the prototype, by showing them the components, the interface, people can visualize how the interface would look like and whether this is something I want, right? But non-functional properties is a very difficult thing for the developers to show to your customer. This only can be done by showing them the architecture. So this only can be done by reviewing your architecture in early phase of the design. So otherwise, you need to wait until towards the testing phase of the development to finally find out whether your system has satisfied the non-functional requirements. It would be too late, right? The rework cost will be escalating terribly. So the non-functional requirements are the results of architecture choices. By comparing different architecture choices you're making, you actually you are playing a trade-off between different non-functional requirements, because different architecture choices, alternatives, provides different non-functional properties. And not all non-functional properties will be supported well by all kinds of architecture choices. So you have to help the customer to make the trade-off. Which one do you want? Which are the highest priority non-functional requirements? So non-functional property questions are now raised as the comparison between architecture alternatives. And the specification of non-functional property might require an architecture framework to even enable how you are going to stage. So what kind of upper bound and lower bound you are going to define for specific non-functional requirements. So by showing the evidence, you are kind of mitigating the risks of not achieving a specific non-functional requirements at the end of the project. So an architecture framework will be required for an assessment of different kinds of to-play trade-off analysis of whether the non-functional properties are achievable or not, and which ones are the highest priority, which ones can be deferred to the later phase of the development. So if you are interested in knowing how architecture can play the role in the non-functional requirements assessment, there is a very classic textbook in the software architecture domain, which is also authored by a group of researchers in the Software Engineering Institute affiliated with Carnegie Mellon University. So I remember one of the authors, Professor Lambeth, who is currently leading the software engineering group in the NICTA in Australia. Okay. So by looking at the role of architecture in the software requirements, there is a very famous model which is called Twin Peaks model, which shows the co-evolution, the co-development of software requirements and the software design and architecture. So the Twin Peaks model are drawn from two dimensions. So we are showing the implementation dependence between the requirements and architecture design. And we are also showing the level of details, the evolution of level of details in the software system development. So we can tell that the system is evolutionary, adding details based on the availability of the information. So the information are not coming from nowhere. They're coming from the evidence we're collected from our design. And the implementation dependence are established between requirements, design, and even to the future code and test cases, so that we establish some kinds of traceabilities across the artifacts that are generated by different activities of software system development. Okay, so after we discussing the roles of software architecture in the requirements acquisition phase, we will look at the architecture in our design phase. It's very intuitive because everybody accepts this. Design is an activity that pervades software development. Design doesn't start from the design phase. It starts from the domain analysis, starts from the domain understanding, starts from the requirements acquisition. So it's a major phase that creates the main parts of the software architecture, but it's not the unique phase which creates the software architecture. And it's typically in the traditional software development process, the traditional design phase decisions concerned with the structure of the systems, right? The identification of its primary components, the main components, and their communications, their interactions. And architecture denotes the set of principal design decisions about a system. So which means architecture doesn't capture all the design decisions. And we're going to talk about what can be considered as the major design decisions, what are not. But the design and architecture, the architecture especially, is more than just the structure. It's far more than just the structure. We're not going to show just the structure of the design, which are typically understood by most of the developers. And question?
Designs are Domain independent?
The design is, yes.
Sorry, that architecture.
Yeah, the design is very domain dependent.
Architecture?
The architecture can be domain dependent, and part of the architecture cannot. It may not be domain dependent. You will see it when we discuss the components and the connectors. Yeah. So the only unique characteristics we're going to discuss in this course is the architecture-centric design. So the traditional design phase suggests we are translating the requirements into the code, into the algorithms, right? So developers immediately will jump into the selection of a specific algorithm when we take the requirements from the stakeholder. We're going to immediately determine what kind of tool, implementation tool, we're going to use, what kind of language we're going to use, right? And what kind of operating system platforms, database system platforms we're going to use, and what are the most efficient algorithms to fulfill these requirements. So the programmers will jump into the code and test cases. So this is a very common practice, even in large software organizations. And but the architecture-centric design emphasizes different aspects of system development. We start with emphasizing the stakeholder issues, the stakeholder concerns, and then we emphasize the determination, the decision about the selection, assessment of a specific set of cost components. And we are emphasizing the overarching styles, the structures that can guide, that can rule your design, and how you're going to modularize, package your system. What are the primary class structures? And we're considering the future deployment of your system. So we're not going to only concern about the correctness of the system, the correctness, the performance of your algorithms, but we're going to consider, we're going to put your system into your future deployment environment when we design, when we architect the system. And we're going to consider the post-implementation and the deployment issues, including the maintenance, evolution, the scalability of the system. Okay. So another important techniques we're going to discuss in the design phase that most of our developers are very familiar with. So in order to support the traditional design, we have leveraged, we have already devised a set of design techniques and tools which have supported through our software engineering design activities, which we are very familiar with, right? So we basically, the current basic conceptual design method and the tools can be categorized into 2 or 3 categories. So basically, we classify those conceptual tools which are supporting our design into separations of concerns, modularity, and abstractions. So basically, we could, sometimes people consider the modularity is for the separation of concerns, right? So those 2 can be combined together. And the other thing is how we are going to determine the abstraction level of your design and architecture. So we have 2 very intuitive, illustrative, widely adapted, widely used strategies and the tools which has been supporting our design activities. The very basic one is object-oriented design techniques. And the other one is called domain-specific software architectures, which is closely tied to a specific application domain. So let's take a look at each of the tools and the techniques which we have been experiencing in our design phases. So the first techniques most of us are very familiar with are object-oriented design techniques, because most of us are familiar with object-oriented programming languages, right? Even though the programming languages is still different than object-oriented design. However, the object-oriented design inherited a lot of basic concepts and ideas from the object-oriented programming languages, but in a different abstraction level. So object-oriented design devices, they have a very unique kind of components, which is called objects. So objects mainly capture the abstraction entities in the real world. So objects are usually mapped to the real entities in the real world. Sometimes it doesn't. We can create our own abstract objects. For example, the transaction may not be tangible. In the banking system, may not be tangible, but they can be objects. And the objects encapsulates the state with the functions, with the capabilities, with the attributes for processing and manipulate the state changes of that objects, right? So when we talk about objects, when we execute the system, we actually observing the change of states, which eventually which is manifested as the system behavior. So the object-oriented design techniques that was proposed by the OMG community, so Object Management Group, which is a community who proposed and supporting the object-oriented design. The major contribution of proposing the object-oriented design is not only inventing creation of different kinds of object-oriented language, but also it actually provide a very universally accepted modeling techniques, which is called unified modeling language, which helps us to visualize and analyze the software design in an object-oriented way. And by creating object-oriented design, we have accumulated a set of design patterns which we can reuse again and again across different application domains, right? It's not constrained by application domains. Then we can reuse those design patterns. So those are the major contributions that are brought by object-oriented design techniques. But by observing, understanding their pros, we need to understand also their limits. So what are the limits of the existing object-oriented design techniques? First, they provide only one level of abstractions in this case. One level of encapsulation, which is the object, right? Everything is modeled as objects. But it limits our view if you are looking at the current distributed software system development, right? So if you are looking at the cyber physics system, so everybody in the future, everybody can be the IP in the world. Everybody wears the iWatch. So people may locate where you are easily. So you can be one object in this network, in our system. And we would like to, sometimes we would like to define who are the user agents, who are the servers in the system. But the object cannot help us differentiate those kind of distributed objects, right? So by only using object as the level of encapsulation is far less sufficient for us to model the current needs of distributed system development. So this is distributed system development is just one example. We also have embedded system development, which object cannot be used to model everything, to differentiate every entities, every elements in our software systems. And by limiting our encapsulation into the objects, we only support one kind of interface, which is called method call, right? So in our object-oriented design, we only use method call to support the communications between objects. But this also imposes a lot of limitations in the future evolution of the system. So in the distributed system, the communication are not implemented only by method calls. So we are connected by different kinds of networking devices, the channels, different kind of channels. So the one notion of interface is far less sufficient. And there is one type of explicit connectors, right? So this is tied with the unique type of interface that are supported by the objects. So even the message passing is realized through a procedure called, sometimes it's not efficient, it's not effective to support the reuse migrations of the components. And on the other hand, when we talk about object-oriented design, naturally, we will think about the language we're going to use, right? So naturally, we will choose the object-oriented language to implement our system, because this object-oriented language seems to be the only compatible ways for us to implement our systems. So by choosing the object-oriented programming languages might dictate some important design decisions, because due to the limits that are imposed by a specific Java programming language, each programming language has its own limitations, implementation limits. Because, for example, Java has a very strong typing requirements, very strict type requirements. So those kind of things may restrict your view, your methodology of design your system. So in the future, not all our system is going to be designed by object-oriented programming language, right? So this is so in this class, for our final projects, we do not require each of you to use object-oriented programming language to implement your system, because I give you sufficient amount of freedom in choosing different kinds of tools, components, connectors that you could leverage in the Word to design and implement your system. So you are free to choose any kind of implementation techniques you're going to use, as long as your techniques well justify and support the properties of your software architecture. So an object-oriented design assumes a shared address space. So this also imposes some limitations to evolve our design, evolve our architecture to support the future cyber physics system, the distributed system, the grid-based system. So by assuming, or originally, when object-oriented language was created, it assumes the shared address space, and it has a lot of internal housekeeping support for the heaps, stacks, those kind of shared address space construct or elements in object-oriented programming languages. Even though some people may argue that Java can support multi-threading, right? But it's actually an afterthought development after the original creation of the object-oriented programming language. So even though it can support multi-threading, it's still insufficient for us to differentiate different communication patterns, different communication styles, different behaviors that are manifested by our distributed systems. So those are the major limitations that are provided by the object-oriented design. So by observing, by understanding those limitations, then people thought about, another thing which might not have been listed here in object-oriented design. I don't know whether you have experienced that the object-oriented design techniques may not carry over the domain knowledges. So it carry over the programming implementation knowledges, more application knowledges, more than the domain knowledges. So basically, it does not carry too much domain level, the abstracted level informations that can be reused in a specific domain, application domains, right? So because the object-oriented design only are represented by the objects, classes, right? But they do not capture the context. Do not capture it. There is no efficient way for us to capture the contextual information of the components, of the connections between the components. So it does not well capture or carry over the domain knowledges, the domain context, domain information. that also needs to be reused as one of our valuable assets in our future development. So then people thought about how can we carry over the domain knowledges. So that brings up the DSSA, the domain-specific software architecture. So the DSSA is created to capture and characterize the best solutions and the best practices from the prior experience, prior projects within a specific application domains. And the production of new applications can only focus on the variation points or the novelty or the actual innovations of those evolution of the products. So that keep our developers focus in only developing, perfecting, and testing our new variations of the products, our novel innovations. By reusing the applicable parts of the architecture and implementation, we actually propose a product family. We actually developing a product family which can carry over our prior domain-specific software development experiences. So when we talk about DSSA, most likely we're talking about product line architecture and product families. So we already discussed the Philips Koala example, which governs the current small electronic system development. And then after we discussed the basic design tools, the basic design principles, the separations of concerns, the modularity, the abstraction, then we would like to discuss how the software architecture plays the role in the implementation. So the objective is of architecture in the implementation is to create an executable in the hardware platforms, right? So what are the major roles that are played by software architecture in the implementation? So our main objective is to make our implementation to be faithful to the architecture. So why do we want the implementation to be faithful with the architecture? Because the future evolution, the future changes are most likely initiated from the code. We always start our change from the code, right? And we always carried a very good intention that after we modify the code, we will go back to adapt our architecture to the change the code. But unfortunately, those good intentions were never or seldomly fulfilled at the end. So the code, we would like the code to be as much faithful to the architecture as possible along with the development, but it's not always feasible along the system development. Sometimes we could accommodate, we could tolerate some inconsistencies or intentionally keep some inconsistency between the architecture and implementation. And we would like to know, because we know it's very challenging to always keep the faithfulness of architecture with the implementation. So it's always a topic for us to learn how much adaptation is allowed, how much consistencies we need to keep, we need to maintain along with the development, because it's very effort-consuming, it's time-consuming, it's cost-consuming. It's very costful to ensure the faithfulness. So in this case, we would like to differentiate what kind of changes are architecture relevant and what kind of changes may not be relevant to architecture. So you will know, so we will define architecture as the major design decisions that are carried by our design. But so this is why we didn't include all the design decisions, because we don't think all the design decisions are important for software architecture. So it must fully develop all outstanding details of the application that are defined in our architecture. So fully developing all outstanding details means we need to implement all the required structures, required components and connectors that are defined in our architecture. But it's also illegal for us to introduce additional ones that has never been introduced in our architecture, right? So introduce an actual features may not be a good thing for our development. It may violate your original design intention. So let's take a look at what are considered as a faithful implementation. First, all of the structural elements found in the architecture should be implemented in your source code. And source code may not utilize major new computational elements that have no corresponding elements in architecture. So adding actual features does not do good for you. And the source code must not contain new connections between architecture elements that are not found in the architecture. So these are basically the definitions for a faithful implementation. Those are the rules we're determining whether it's a faithful implementation or not. So after we understand the faithfulness of implementation, then we will consider whether it's a feasible thing we can always enforce, right? Is it realistic? Or is it really overly constraining our development? So what if we deviate from the architecture during the implementation? It's very normal. We will see the deviation between the implementation and the architecture. What we should do, whether we should keep those deviations or not, and whether we need to fix them immediately. So this is something we need to discuss in the future. So after understanding what is faithful implementation, then we will ask what are considered unfaithful implementation, right? So those are not complementary concept, actually. The implementation does not. The implementation does have an architecture, and however, the architecture may be latent into the implementation, as opposed to documented. Especially in agile system development, people do not specifically specify documented architecture, but architectures are in the developer's mind. So failure to recognize the difference, the distinctions between the plan and the implemented architecture will incur a lot of side effects to the future system development. So what are the disadvantages? What are the failure we could encounter, we could accept after too much deviation between the implementation versus the architecture design? So considering in the future, you're going to deliver your product to the next team who is responsible for maintaining your systems. So you are the developer which have already completed your task by delivering your system to your customer. What about their maintenance team is going to take over the system and evolve, adding new features, maybe tailoring to their current systems? By looking at their tailoring, most likely will start with your code. If you do not have consistent specification of your architecture and the code, most likely they're going to change their system in an unattended way in the future, right? So definitely, their change may incur a lot of unexpected defects or leading the product to an unexpected evolution path. So, question?
For example, let us consider the architecture is built and the source code is, the developers have started working on it. Yeah. And later when a stakeholder come up with the new requirements, does the developers accept that architecture? Accept that requirements. How, if they accept, how they are represented in the architecture?
Exactly. You brought up a very good point, which you are ahead of me, because I'm going to talk about when you accept a new requirements, right? Even though the same team, so it's inevitable for our current organization to have a high team developer volatilities throughout the development, right? I just heard there is a rumor that IBM is going to lay off like over 110,000 people. And so it's almost 25% of their current workforce. I don't know whether it's true or not, but it's a tragedy. But such a high volatility rate imposes a big challenge not only for our worker developers, but also for our industry organizations, because you're going to have some new hires in the future to take over your current systems. So you're going to evolve your system by taking the new requirements, new features, and retiring the existing features. If you do not have the consistent architecture documents, specifications with your code, most likely the change is not going to evolve. The change is not going to be made in the expected way. So they're going to have a lot of misunderstandings, confusions about the results of their changes when they execute their system, test their system, versus their intended requirements. So, and on the other hand, they're going to determine whether the new requirements is actually feasible or compatible with the existing features. But if your implementation is incompatible, is unfaithful to the architecture, how they can correctly assess, accurately assess the feasibility and the compatibility of the new feature as against with the existing features, right? So it will provide a lot of misleading information for all the stakeholders, including end users, including customers and the developers, regarding what they believe and what they have seen. It could make any development or evolution strategy that is based on the documented but inaccurate architecture doomed to the failure. So no matter whether they try to evolve the system based on the documented architecture or whether they evolve based on your implementation, the system will be very inconsistent. So it will incur the failure of the future system. Okay. So I think time is almost up, and I will leave a few minutes for any questions, concerns, comments for this course. So one thing I would like to talk about in this class is I already received some emails from the students coming from 2 of my classes, because I'm teaching 2 classes this semester. Unfortunately, both of them are design classes. So please identify your course number when you try to raise a question or communicate with me through emails in the subject. So please identify yourself as a student in CSE 7319 or the CSE 83A13. So otherwise, yearly, some students are taking both of my classes, especially. So please identify yourself with your course number so that I can better understand your questions. Well, sometimes I feel very confused about, maybe. So if there is no questions, then I'll see you next week.